Offshore wind farms are an integral contributor to the global need for a sustainable, low-carbon future. These complex systems operate in challenging, dynamic, and remote environments, with new wind farms increasingly being constructed in deeper waters further from the shore. The operation and maintenance of these critical systems represent a significant cost throughout the life cycle of the wind farm. The integrity of energy contribution from offshore wind farms is dependent on many critical components, for example wind turbine blades and subsea power cables. These composite structures are challenging to access and are prone to a range of different failure modes. The structural complexity hence also presents significant issues to asset management. In this video, we are going to describe and demonstrate the latest research findings from our Heriot-Watt Smart Systems group, which proposes an innovative fusion prognostics approach on offshore asset management. We utilized advanced sensing technology to gain access to previously inaccessible data. We created multi-physical models to advance our understandings of the interdependent factors that influence the overall state of health. We created machine learning models of new data streams, which are secured through the use of robotics to conduct integrity assessments to transform asset management and planning of these key components to offshore wind farms. The initial phase of our research was centered around improving our understandings of subsea power cable failures. We conducted failure mode, mechanism and effect analysis, which involved a detailed review on 15 years of historical data. Interviews with operational engineering staff also provided insights into current maintenance and installation practices, therefore identifying available information, data and priorities for the engineering team. We developed a multi-physical model to calculate damage and predict lifetime along the length of subsea cables due to environmental conditions. This model can be tailored to regional or specific environmental conditions and cable properties. The model can also be customized to capture specific features like zones of previous cable repairs and sections of the buried cables, etc. This model will simulate cable movement, the process of scouring, and calculate the volume loss of cable wear that will occur over time due to both abrasion and corrosion. A cable failure occurs when the protective layer is worn out, and that will give us the remaining useful life prediction of cable route. The majority of cable monitoring systems are focused on internal failure modes. Our review of data indicated that 70% of failure modes were due to external factors, namely abrasion, corrosion, and third-party impact. Currently, there are no technologies available to undertake detailed and in-situ assessment of subsea cable integrity. Our research shows that advanced low-frequency biosonar technology can be used to provide a cross-section analysis of subsea cables, thereby enabling it to obtain various cable information relating to the thickness of constituting layers that would then correspond to different degradation stages. We applied different machine learning techniques which can classify cable samples with different types of failure modes. It can also classify different levels of damage due to abrasion and corrosion at differentials of 5 mm. The multi-physical and data analysis model mentioned above have been coded and implemented into a cable health management system. In this system, the cable installers will be able to estimate the expected life of a cable. The estimation is based on input knowledge of environmental conditions such as tidal flows, seabed conditions, cable specs, armor material types, and the results of sonar integrity data analysis. A user can access and manage the cable armor material data in the material management module. It allows the user to input and install material specifications. In our model, an abrasion wear coefficient needs to be identified for layer materials in the cable when subjected to different seabed material interfaces. In our database, we calculated the wear coefficient using an offline table test. Other associated properties like density and hardness are also obtained from the cable manufacturer. The cable management module allows users to store or edit cable specifications data in the database. Here is an example of adding a Nexans high voltage subsea cable. End user would need to input different properties like overall diameter, weight in water, as well as the armor structure of the specific cable, such as the number, thickness, and types of different cable protective layers. Those mentioned, as well as the material specs, will be used for further remaining useful life calculations. The route management module allows a user to create or manage cable installation route plans and conduct lifetime analysis. Normally, a whole route contains several cable segments. Once the user inputs the start and end points of the route, we can start designing the deployment by gradually adding different cable segments. Configurations like length of cable segment, tidal flow profile, seabed type profile, types of cable buried depth, etc. also need to be added. Once the setup is finished, The installer can estimate the failure time of every segment in the whole route by applying our RUL prediction model. The users can also see a comparable presentation of the RUL by selecting different types of cables. This system can be used to predict the RUL of existing subsea cable installations and can also support optimal route and cable type selection for a given installation. Repairing and replacing cables are costly. It is therefore essential for offline operators to conduct careful planning to maintain cable integrity. In our system, a user can easily manage the cable inspection missions by using the inspection management module. After setting up the date, time, and AUV for new inspection missions, users can view and manage the inspection tasks in a holistic calendar. When an inspection task is finished, the integrity data obtained from the sonar embedded AUV can be used to upgrade the offline RUL prediction results. The user can apply different machine learning analysis model on the latest data to get more accurate cable integrity status, for example the change of dimensions, and to further update predictions on potential future failure modes, failure time, failure locations, or segments. The updated results also include system suggestions of the next mission plan regarding time and notable cable segments. The system provides a new insight into predicting and localizing cable faults with sections of cable spans. It also provides means of identifying optimal cable products and installation routes, therefore reducing risk and O&M costs. FMCW radar sensing is a suitable candidate for detailed non-contact and non-destructive analysis of composite structure. The major advantage of FMCW is the ability to penetrate low dielectric materials and return data relating to both surface and subsurface failure modes. The radar can be deployed at a range of distances from the turbine blade, and through highly tunable sensing we can provide a rapid cross-sectional analysis of the wind turbine blade. This sensing technology has been patented by Heriot-Watt University and is now available by Microsense Technologies Limited. Wind turbine blades are constructed using a range of composites, epoxy resins, and adhesives, which make these blades very susceptible to many types of failures. Currently, there are no non-contact techniques to assess the internal integrity of wind turbine blades. FMCW radar sensing in the K-band is particularly sensitive to defects such as delamination, cracking, and water ingress. Therefore, the team at Heriot-Watt University have looked to address these issues by designing experiments using the decommissioned wind turbine blade samples. The experiments performed thus far have validated that FMCW radar is capable of detecting water ingress and delamination which are not visual to the surface. FMCW radar sensing enables engineers to obtain more information about the integrity of a blade and therefore can assist in predictive and scheduled maintenance of the asset. This will reduce downtime of the asset and reduce the risk of permanent failure. We extended the utilization of FMCW sensing to the detection of corrosion under installation for assets that have external dielectric protective coatings, for example paints and polymers. We have verified that we can detect the precursor onset of CUI in the form of oxide formation, pitting, moisture ingress, as well as metal loss. The FMCW was mounted onto a ClearPath Husky A200 wheeled robotic platform with two integrated UR5 manipulator arms, which can perform targeted and holistic scans of metal infrastructure, where the metal is exposed or coated in a low dielectric protective material, paint. The UR5 arms were programmed to complete a raster scan whilst holding the FMCW radar sensor 10 cm from the target material. The results found that there is a distinct difference in the reflected electromagnetic wave for varying defect types. FMCW radar sensing represents an advancement of non-destructive testing methods for the detection of composite material properties as well as failure modes. The advantages offered to the offshore renewable energy as well as the civil and nuclear sectors are significant, as this NDT method isn't affected by mist, fog, smoke, and is capable of detecting defects invisible to surface inspection from a safe distance. The K-band FMCW sensor is versatile and can be coupled alongside advanced digital analysis and digital twin systems. The further development of digital twin systems will enable accurate monitoring of faults, defects, planning of maintenance, and remaining useful life of assets.